Hi, my name is Akin Hyatt.
Hi, my name is Lauren McCaffrey.
This is our Lab 5 video summary. In an ideal optical system, spherical waves are always imaged as spherical waves through a lens, but when on-axis spherical wavefronts are incident on a spherical lens, the rays near the edge are refracted more than those close to the center. We call this phenomenon spherical aberration since it is an inherent property of spherical surfaces. If we zoom in on the focus of a spherical lens, we see two extreme foci, the marginal focus and the paraxial focus. We can characterize the amount of spherical aberration in a system by measuring the distance between these 2 points, which we call longitudinal aberration, or by measuring the size of the spot at the paraxial focus, called transverse aberration. The Hartmann mask technique allows us to measure both of these characteristics by showing the behavior of single rays, determined by the size and quantity of small holes in a flat plate. By measuring the distance and focus position of each ray, we can determine the longitudinal aberration. Similarly, tracking the deviation in ray location at the paraxial image plane determines the transverse aberration. Since we are only interested in the on-axis aberrations, proper alignment of all optical components is crucial. Our system performance is limited by the quality of the lens mount since we cannot adjust its pitch or account for manufacturing errors. We also need the Hartmann mask to be aligned as parallel to the table as possible. Finally, we use the microscope to find the focus of the lens.
To start taking data, we first characterized the spherical aberration with the lens oriented such that the plano side faced the collimated beam, or the most spherical aberration-inducing orientation. We scanned the beam across the mask with the mirror and observed the movement of the beam exiting the microscope with respect to the crosshairs, translating the microscope along the optical rail until the beam through the extreme and center holes was centered, at which point we knew we were aligned to the marginal focus of the lens. We scanned across the mask again and then adjusted the microscope position perpendicular to the optical rail until the beam was once again centered on the crosshairs and recorded that absolute microscope position with the micrometer for each hole. We followed the same procedures for a lens with a shape factor of 1, or lens orientation introducing the least spherical aberration. This time, however, we observed that the translation of the beam with respect to the microscope crosshairs was much smaller than that for the previous shape factor. Finally, we measured the transverse aberration for a biconvex lens with a shape factor of 0. We once again repeated these measurements and expected that the magnitude of the translation of the beam would be in between what we observed for the previous shape factors. Once we obtained our experimental Rayfan plots, we generated theoretical Rayfan plots in Zemax to compare. To start, we can analyze the results for a shape factor of -1. As seen here, there is a noticeable difference between the RMS spot size when the plano side of the plano-convex lens is oriented towards and away from the collimated beam, which we know is from spherical aberration. In order to obtain good theoretical reference for the Rayfan plots, we needed to determine the most correct entrance pupil diameter, or EPD, given that the magnitude of the transverse aberration is proportional to the EPD as seen in the listed equation. We tested 3 EPD values including 1 inch, 22 millimeters, and 17 millimeters, ultimately identifying the 17 millimeter EPD theoretical Rayfan plot to most closely match the experimental data. This is unsurprising given that the extreme Hartmann mask holes were not at the very edges of the 1-inch mask disc. We did this for both a plano-convex shape factors and found similar fitting results for the Rayfan plot at the marginal focus, where the marginal and center ray bundles were all approximately centered on the microscope crosshairs on the viewing screen. We also characterized the longitudinal aberration experimentally. However, the results do not closely resemble the theoretical data. We believe this may be attributed to the measurement error and uncertainty in identifying the optimal focusing position of the beam, given that the beam exiting the microscope was somewhat dirty. Finally, we analyzed a theoretical model of a lens with a shape factor of 0 and found that the amplitude of the transverse aberration results were in between that for a shape factor of plus and minus 1. However, our experimental Rayfan plot was slightly asymmetrical for this EPD and doesn't match the simulation as closely. Nonetheless, the overall trend of the Rayfan plot at the marginal focus was observed.